Hello folks. After spending 28 minutes recording a video of the entire practice test, all of the practice test problems, and discovering that for some reason my mic wasn't syncing and I had to close ActiveInspire and open it back up in order to make it work, I'm just going to do problem number 6 because that's the one I promised you. So here we go. Problem 6. So we started working on this in class today. We've got our hydrazine reacting with oxygen to produce our nitrogen gas and water. This is basically a combustion reaction, just with without a hydrocarbon now. But it's basically the same idea as our combustion reactions, burning, in this case, hydrazine instead of one of our hydrocarbons. Okay, so in order to use bond enthalpies to calculate our delta H for this reaction, we first need to know what bonds we have. And so we started this in class, drawing the Lewis structures, but for those of you who were not paying attention, let me run through that again real quick, specifically for the hydrazine. So we've got N2H4. First thing that we're going to do with the Lewis structure is we're going to find the total number of valence electrons. So we've got nitrogen has 5 valence electrons for each nitrogen atom, and we have 2 of those. So that's going to give us 10 valence electrons. Our hydrogens each have 1, and we have 4 hydrogens, so that's going to give us 4, for a grand total of 14 valence electrons. Now we're going to draw the skeletal structure of hydrazine. Our nitrogens have to be in the middle because our hydrogens can only make 1 bond each. So we're going to have a nitrogen bonded to a nitrogen. Each nitrogen is going to get 2 hydrogens bonded to it. So there's our skeletal structure with all of our atoms in it, and now we have to count and see how many valence electrons we have used. So we have already used 2, 4, 6, 8, 10, 2 for each bond, giving us 4 left over. Okay? Those 4 mean that we have extras to put on our central atoms. So if we didn't have enough to give our central atoms an octet, then we would start forming our double and triple bonds. But since we have 4 extra valence electrons left over, we put 2 on each nitrogen, and that gives us a total of 8 for each nitrogen, 8 for this nitrogen, and 2 for each of our hydrogens. So everybody's happy, everybody has a full valence shell. So that is going to be our structure for hydrazine. So when we go back to looking at the number of bonds that we have, all right, we've got 1 single nitrogen-nitrogen bond. We've got also nitrogen-hydrogen bonds, single bonds, and we have 4 of those. Okay, so if we go to our bond enthalpies table, Table 11 in our IB data booklet, we look in our single bonds chart and we find nitrogen and nitrogen, and that's going to give us 158 kilojoules per mole. Our nitrogen-hydrogen bonds are going to give us 391 times 4. Okay, and so that's going to give us 1564 plus our 158 for our nitrogen-nitrogen single bond. Now the other reactant that we have is O2. And if you have been doing this long enough, you will just automatically remember, without having to go through the whole Lewis structure, that O2 has a double bond between your oxygens and for two lone pairs on each oxygen, giving everybody an octet. And so we are then looking not in the upper table, but in the multiple bonds section below the table, where we find that we have our oxygen double bonded to oxygen, and we only have one of those, and that's going to be 498. Okay, so in our reactants, we have our 1564, our 158, and our 498 all added together. And that is going to give us a total of 2220 kilojoules. Okay? So these are all the bonds that we are breaking in order to make our new products. Now you'll notice that there is a single bond between the two nitrogens, but there isn't any enthalpy value for adding two bonds to make it a triple bond like our N2 is. So you're just going to assume that you're breaking this bond and forming the triple bond. So just assume that you're breaking all of your bonds in a situation like this and forming a new one. Now if you have a situation where you're just breaking or adding to one functional group in a molecule, then you would worry about specifically which bonds were broken and which ones were being formed, and you would ignore the rest of the molecule that was being unchanged. But in this case, we're essentially changing both molecules. Okay, so we've got 2220 kilojoules as our total for bonds broken. So now let's look to our products. So I'm going to clear this, hopefully. This is going to give us, so we've got 2220 kilojoules over on this side. And now we're looking again at our N2 and our H2O. So as I said a minute ago, this is another one that you'll just memorize when you've been doing this long enough. Our N2 is going to be a triple bond between our two nitrogens with a lone pair on each nitrogen. So that bond is, if we look down at our multiple bonds, is going to be 945 kilojoules. Okay? And then we look at our H2O. And as I'm sure you know, our water molecule Lewis structure is going to have two hydrogen-oxygen single bonds for each water molecule. But notice in our formula that we have two of them. So really, we have 4 hydrogen-oxygen bonds, okay, in this formula. So we have 1, 2, 3, 4. So we're going to look at our hydrogen-oxygen single bond values in our enthalpy table, and bond enthalpies table, and we're finding that it's 463, and that's going to be times 4, okay, which is going to give us 1852, and to that we're going to add our 945 from our N2 molecule, and we're going to end up with 2797 kilojoules, okay? So that's going to give us 2797 kilojoules. So now when we look at the overall equation, we are going to set it up as the delta H is going to be equal to the sum of our bonds broken minus the sum of our bonds formed. Okay? And so that's going to give us 2220 minus 2797, which is going to end up with negative 577 kilojoules per mole. Okay, so if we, I know this question doesn't ask for it, but if we were to draw this as an enthalpy levels diagram, like you had to do in question 5, we would have our enthalpy on the y-axis, and we would start with our reactants. So our reactants are going to be here, about here. This is our, we're going to call this 0 essentially. So this is our reactants. This is our hydrazine plus our oxygen. And in order to break those bonds, we are going to need to add energy. So we have a positive enthalpy going up of 2220 kilojoules, okay? And that takes us to the level where we have all of the bonds broken. So this is not where our products are. This is where we have broken all of the bonds for our reactants and we have not formed any new bonds yet. So this state may not actually exist in terms of the reaction, but in terms of calculating with our bond enthalpies, we can say that this stage we have 2 nitrogens by themselves plus 4 hydrogens by themselves plus 2 oxygens. And now we know that these things don't really exist in real life. You hardly ever have nitrogen, hydrogen, or oxygen by themselves. They exist as diatomic elements or diatomic molecules. So you can tell that, and that makes sense because this is a higher enthalpy level, which means that these are less stable. We are adding energy to bring us to a less stable configuration where all of our bonds are broken. And then when we form the new bonds, our delta H is now negative because we're going down, exothermic, negative 2797. So we're going down even further than where we started at to a lower level. And this is where our products live. So this is where we have our N2 plus our 2H2O. And the difference here is my overall delta H of the reaction, okay? So that is my negative 577. And this may not be perfectly to scale, but you get the idea that in order to get down to these lower energy products, we had to add energy to break the bonds in the first place, and then we gained energy back, or released energy in the process of forming the new bonds. So hopefully that's helpful, and hopefully it's not too late. Sorry about the technological snafus. All right, see you tomorrow.